Yeah, that way I just load it up and you guys can go watch it later.
Right. It's helpful though.
Yeah, I'm also putting them in the local ISM chapter. We're gonna get like a YouTube channel and load them up there or something.
Nice.
All right, so forecast accuracy. We want to measure how accurate our forecasts are. Well, most of us that actually make the forecast don't want to measure that, but the ones that use the forecast would like to measure it. So factors that can affect forecasts. Lead times, fluctuating lead times. Buyers and planners need to work with suppliers to determine the source of the fluctuation. Changing labor conditions, expiring union contracts. Usually these things are all kind of leading to shortages. Changes in financial markets, interest rates make trucks more expensive. So people buy fewer of them, although that hasn't proven to be the case in the last year. Geopolitical factors, companies continue to expand into global markets. So if you're doing business in Africa, it's always a roll of the dice as to whether you're going to get taken over or not. Technology shifts. You see this a lot in software and high-tech stuff. Using the internet to find product sources, that was a technology shift in purchasing. We used to use the books that everybody had to buy. Natural disasters, this can cause shortages and changes in global trade, embargoes, such things like that. Climate conditions, things like consumer spending, business investment, level inflation, unemployment trend, and new construction. All of those are kind of indicators for forecasts. Data integrity, you got to be working with good data. And the bullwhip effect we've talked about before. So small downstream need and supply chain can produce a large fluctuation due to timing, transportation, as well as lot sizing. Lot sizing is usually the culprit. If you look at places like Florida, where they know the hurricane's coming and everybody sells out of blue tarps. So the stores go order a bunch more blue tarps. And when they finally get there, then the hurricane's passed and nobody wants them, and now they're sitting on all these blue tarps. Happened with patio furniture in 2021. Because everybody was working from home, they all wanted patio furniture, so they all went out and ordered patio furniture. And then the stores are sitting on patio furniture and they're trying to get rid of the stuff. That's the bullwhip effect. So measures of forecast accuracy. Types of forecast error. You have two types of forecast error. You have random error, the measure of being wrong on the forecast. Errors are not correlated with one another. So a forecast is always wrong. The random error is what causes that. It's just there's too many things affecting the forecast to know them all. But there's also a bias, which is also a form of error. It's a tendency to forecast higher or lower than the actual value. So if you're always higher or you're always lower, that's a bias. And that's different from a random error. If the average of the forecast errors, which is the forecast minus the actual, is something other than zero, you've got some kind of bias tendency. And we'll go over the tracking signal to try and figure out what that is. So when you measure forecast error, the average or the mean forecast error is the forecast compared with the actual outcome at a single point in time. So the forecast may have been 135 units and the actual was 130 they sold that month, or they forecast 135, so the forecast error is going to be 5. And the errors are summed up over the number of times and then divided by the same number to get the average. This is the most basic way of looking at forecast error. So it's always the actual minus the forecast. And your little math symbol here, summing up 1 to n, actual minus forecast in period I. This is called the running sum of errors, the RSFE, and it's kind of basic to a lot of the formulas that they use for forecast error. The average mean of forecast error that we just talked about is the running sum divided by n, whatever n is here. Then you've got the mean absolute deviation, or the MAD, or the mean absolute error, less common. This is calculated the same way as the average error, this one, but takes the absolute value of the sum. So the measure of dispersion, it's a measure of dispersion like a standard deviation, but more robust since outliers don't affect it as much. So this is the MAD here. You can see it's actual minus forecast sum 1 to n over n, but it's the absolute value. It's not the sum. So that's the MAD. Then you've got the mean squared error. This is a measure of total error to be expected for a sample estimate. Forecast error is calculated and squared to get rid of the negative numbers. So you're just doing the running sum of forecast errors, but you're squaring it to get rid of the negatives. Instead of in the MAD, you're using the absolute deviation, and you're dividing by n. So that's the mean square error. And then there's the MAPE, is the last one I think we're going to look at. Summing the percentage forecast error for each period. So actual minus forecast, which is the same as you got here, divided by actual. So you're dealing with a percentage instead of a raw number. Then dividing by the number of periods like you do here, and subtract the answer from 1. This gives the forecast an idea of the true magnitude of the error because you're dealing with percentages. Also allows for comparison of forecasts using different scales. So under here, under the MAD, if you got different scales, one's in time and one's in temperature, you can't really compare them because it's losing the numbers. But on a percentage basis, it's more comparable. So it's the same thing, running sum of forecast errors divided by the actual. You're taking the absolute value of that, and then you're going from 1 to n, and then you divide by n, and then you subtract that from 1. That is the MAPE. It's a very common error calculation used. And then the tracking signal. This is what's used to see if there's biasing in your forecasting. So dividing the running sum of forecast error by the MAD. So the RSFE, if you go back here, running sum of forecast errors, we're going to divide that by the MAD. And that's going to be your tracking signal. Looks like this. There's running sum of forecast errors, and then the absolute value is the MAD. That will be your tracking signal. If it's equal to 0, it's actual demand. So tracking signal equal to 0 is actual demand. A tracking signal less than 1, so it's negative, indicates the actual demand is less than the forecast. So you're tracking high in the forecast. If the tracking signal is over 1, it's the opposite. You're tracking low in the forecast. So a tracking signal of plus or minus 4 is usually used for high volume inventory items. So they don't look at tracking signals of less than 4. Usually it's insignificant if it's less than 4. And then you've got measures of forecast accuracy, the standard error of the mean. This is not a real common one, but when a population is normally distributed, the standard error of the mean can be estimated dividing the standard area of the sample means by the square root, which is standard deviation divided by the square root of n. So to calculate the standard deviation, find x bar and n, the size of the sample. Here's your standard deviation formula. It's the same thing, x minus x bar squared, and then the sum to n. Then you divide by n minus 1. This is basic statistics. It's a simple way of calculating a certainty of a forecast can be used. So this is the reason you use this standard error of the mean is you want to put confidence intervals around it. So 95% confidence is 1.96 times the standard error of the mean, which is basically 2 standard deviations or 95.4%. So it's 2 sigma. Go all the way up to 6 sigma if you want, but most people will use 2 or 3 sigma. Say they're 95 or 99% confident that the standard error of the mean falls within there. So here's 2 sigma or 1 sigma, 67%, 2 sigma, 95%, and then 3 sigma is 99%. And it goes out, you can go all the way out to 6 sigma if you want, but they don't usually do that. It's an estimate of how far the sample mean is likely to be from the population mean. Whereas the standard deviation of the sample is the degree to which the individuals differ from the sample. So with the standard error, that mean you're trying to estimate the sample mean, not, or the population mean, not the sample mean. All right. Consider the forecasted and actual sales results over 1 month of an organization's top 5 SKUs. So you got forecast error, you got actual and forecast, and you got the gadgets here, and you sum it up for 164. So this is your running sum of forecast errors. Using the mean absolute deviation, what is the best approximation of forecast accuracy? So we have to go back here and find our formula, which is down here. So we would want the absolute value of this and then divide by n, which these are all positive, so I think it would be okay. Divide 164 by n. Let's see if that's the answer. B, MAD would be 3820, which equals 164, and then 164 divided by 5, because you got 5 gadgets, which is 32.8. So it's not that hard. And then let's look at one more here. The average difference between the actual demand over n periods and the forecasted demand is known as the what? So actual minus forecast over n periods. So you're dividing by n. Should be mean forecast error, because actual minus forecast is your running sum of forecast errors. Over n would say divide by n. Let's see if that is the answer. Yep. Mean forecast error equals the sum of the actual demand minus the forecast demand divided by n periods. Okay, so we got 5 questions out there on the chat. You guys go get on them, and we'll go over them at 3:50 unless everybody's got their hand raised, and then we can go over them earlier. Go ahead and get after them.
think we're all done, Rick.
Oh, okay. Aaron, are you done?
Yes, I lowered my hand. Yeah.
Okay. Let's go then find my answers here. All right. Number 1 is A. So basically all you got to do on this one, it's already summed up for you. And you got 5 gadgets, divide 88,000 by 5, and you get 17.6. 2 is B. Bravo. Ethnic diversity is not going to affect the forecast. 3 is Charlie. We've had this one before. Random sequences are not part of time series analysis. 4 is Charlie, because the MAD makes up the denominator of the tracking signal. So if we go back to here and look at it, we've got the running sum of forecast errors over the MAD. So if the MAD is going to be a large number, so it's likely to be large, this should create a large positive or negative above the 4. One exception would be the errors offset one another and somehow being equally positive or negative. So it's basically what's the denominator in relation to the numerator. And then 5 is Bravo, because the mean absolute deviation equals the value of the sum of the actual demand minus the forecasted demand divided by n periods. It's the absolute, MAD is the absolute value, where average mean error is just summed up. All right, any questions? Tomorrow, we've got some more videos, and I even learned how to turn the things on. So we got forecasting techniques for intermediates, some seasonality, and some other stuff like that. So talk to you guys then.
Thank you.
Thanks.
Thank you, Rick.